touchy HDMI cable. All right. If everyone is ready, I can start. Everyone in the back can hear me? Okay, cool. All right. Welcome to the first session of the 2025 EE workshop, hosted by the IEEE UBCO student branch. An introduction to who we are. We are a small group on campus comprised of electrical and electronics engineers and some computer science students and everything else that put together a hackerspace for students to be able to go to, learn, work on projects, and so on and so forth. We're located in EME 2245. Yeah, and usually the hours are posted outside the door, if not on our Instagram. A bit about who I am. I'm a fourth-year undergraduate electronics engineering student. I've got work experience and hobby experience with analog design, RF design, manufacturing, and just general prototyping projects such as. And then yeah, I enjoy working with analog circuitry, radio stuff. I'm an amateur radio operator, so I'm in that world of hobby too. And then other stuff, I like the outdoors. I like quadding, off-roading, that type of thing. The agenda for our workshop, we're going to have 3 sessions. The first session is today, the second one is tomorrow around the same time, and then the third session is on Saturday from 12:30 to 2:30, I believe, somewhere in there. 12. Okay, cool. Yeah, so in this session we're going to kind of go through an introduction of KiCad, of circuits, schematics, and so on, and then we'll get started on the schematic design in KiCad. So, to start, what are schematic diagrams? Like all engineering designs, we have to start with a drawing that portrays what we want to create, what it is that we are creating, and how the system is put together. In electrical engineering, schematic diagrams are used to define the connections between each component, and then describe details for manufacturers, like what kind of part it is, or what kind of part is used, and what value of parts we have. And yeah, it's likely you guys have seen a circuit schematic at some point, I'm sure. So, creating a schematic, you can write them on a napkin if you want. But being that they're engineering drawings, we try and make them a little bit tidier. So yeah, you can draw, or you can use computer software to do it. And in this case, we are using KiCad. There's a whole bunch of other EDAs, as they're called, electronic design automation softwares, such as Altium, or I think there's Easy EDA as an online one as well. KiCad is nice. It's open source, free, and as much as people say it's an amateur sort of software, it has been used at various startups as well to kind of have a good starting point for their designs. So KiCad, as I explained, you can draw schematics, you can create bills of materials, so that would be like a list of all the parts you're using, as well as do the PCB layouts themselves and export manufacturer files, send them off, and have your board built. In addition to the base functions, they supply, or they provide, the community, I should say, provides a lot of Python integrated sort of plugins. In addition to that, you guys can create your own plugins as well. Almost everything you need to know about KiCad can be found on their docs, like documentation page. So there's that. Yeah, so let's run through the application. I take it everyone's installed it and they have it ready. I do not know which version is the most recent, but I also recently installed it, so let's start. To start, you open it up. I'm running 9.0. On my home PC, I run 8.0. Sometimes I update, sometimes I don't. But Yeah. So to start, you have your project overview dialog window here. In this window, you're able to create projects or create templates or create a project from a template. You have a lot of options. In addition to that, you are able to open up a schematic. You can edit a list of symbols. So for every part, you'll have a symbol on your schematic diagram, and if you ever need to make a custom symbol, you can do that. You've got your PCB editor, so that's where you would take your schematic, all the parts, all the connections, and then translate it over to a PCB layout with all the traces and vias and holes and all that. And alongside the PCB editor, you'll have footprints. So kind of like symbols to a schematic have that relationship. Footprints and PCB design stuff is the same thing, where a footprint is the physical sort of how the part is set on your circuit board. So surface mount components will have two rectangular metal pads usually that you'd solder your component to. And then when we export our PCB design, it'll be in a format called Gerber, which is a standard manufacturer file format. The Gerber viewer does what its name implies. You're able to see what that manufacturer file looks like at every layer, which we'll get into sort of later on. One neat tool I actually use quite often is the image converter. The image converter allows you to take an image and convert it to, say, a silk screen pattern or whatever, so you can put it on your circuit board and it can be printed onto it. So if you have, say, a touch mark or a maker mark or brand or whatever that you want to put on the PCB, this would be a good way to do it. Calculator tools, we won't use this, but if you ever do more advanced designs, I'll run it. You can see you can do voltage regulator calculations, resistor calculations, so if you need like a specific resistance value, you can calculate combinations to get that. Electrical spacing, this would be for higher voltage circuits. You want to make sure your traces are kind of a distance apart so that they don't arc or have any leakage between them. Via sizing, most of the track width and via sizing, this is for if you want to run a good amount of current through them. You want to size them correctly so they don't heat up too much. Additionally, there's some impedance stuff for RF. And then we've got the track width, you've got fusing currents, cable sizes, whole bunch of stuff, even transmission lines. So that is a fun one. And then we've got our drawing sheet editor. I've not really used this as much. And then of course you've got your plugin manager here for if you have various plugins. I think, yeah, that's pretty much the overview of our project dialog here. Let's see. Yeah. All right. I think it would be good to hop into our project then. So today we are making what looks like a very elaborate maybe circuit to some. This guy's just an XOR gate in transistor logic using 3 BJTs. I won't go into the technicalities, but trust me, it works. Actually, I think I have, yeah, a video of a prototype on a breadboard. So if you guys are familiar with an XOR gate, it will, nice. It'll light up the output if only one of the inputs are on, but if both inputs are on or both inputs are off, then you'll get a 0 at the output. So, yeah, I think that means we should hop right into it. What happened to my KiCad? There it is. So, to create a project, I'll go to File, New Project. You could also just use Control-N as a shortcut. And And when you create this project, it'll ask for a folder to create it in. I'm just going to create a folder, Workshop 25. And then I'll name this TTL XOR. And save. So now that that's created, we'll have two files. One of them is our PCB file. We'll get to this later on. The first one we want to focus on is our schematic, because you can't create a PCB without a schematic. So once everyone has that, I'll open this guy up. You can double click here, and if you're on a new installation, it'll pop this window up. Yeah, I'll go with the recommended. Okay. And then, if everything goes well, boom, we have everything here. So KiCad schematic editor is sort of a hierarchical editor, meaning you'll have sort of a root page, and then every page is sort of a building block. So if you think of a block diagram, you'll have all your different sort of units, and within each unit is a smaller schematic. We won't get into that because our schematic will fit on the main page. But if you are interested in looking into the hierarchical sheet layout, the docs has a great explanation on it. So with that, I'll just close out of this. Properties, I'll show you how to get to that later on, and boom. I like the larger window. Of course, it's a preference, not a requirement. Not a very good HDMI cable, is it? There we go. Okay. So let me explain what everything does here. You've got this box displays the grid. If I zoom in, you'll see faintly there's the grid. That enables it. I always have it enabled. It gets very confusing if you don't. You can switch between your units. We are in metric most cases, but in PCB design you'll see mils as well, which is 1/1000th of an inch. 2.54 millimeters. But we'll stick with millimeters. One thing I do enable all the time is my cross hole window crosshair. Just makes finding the cursor a lot easier. And lining things up sort of further out, you know, for those who are particular about that, like me. What do we got here? We've got hidden pins on schematics symbols. Depending on how the footprint is, you might have hidden pins on there that aren't used in the schematic but are used on the footprint, and to make it functional in the software, you've got hidden pins. If you need to see those, you can select that. Otherwise, it's generally not needed. We've got our different line modes. This one would sort of be a free draw kind of thing, while this one limits to 90-degree angles only. I typically keep it on that, but sometimes you'll have a design where you want to have an angled wire. With schematic design, we try and keep it 90-degree, but to each their own. And then this one is for 45-degree cases, so maybe you'll have like some sort of crossed wire design. I keep it that. And then we've got our, I'll get into reference designators, but this allows automatic annotation of reference designators. I typically keep it on. Sometimes you can disable it and have all your reference designators done manually, or I think there's a function in here that allows you to select how you want the reference designators to be annotated. But yeah, so that's all those items. On the top, you've got your really basic stuff. It's all your zoom and everything else, print. I usually work with shortcuts. If you hold control and use the scroll wheel, you move to the left and right. If you just use the scroll wheel, you zoom in and out, and if you hold shift and use the scroll wheel, you move up and down. So that's pretty much all of these here, all in shortcuts. And then we've got our shortcuts to all our other software or application stuff within the suite. So if we want to go from the schematic straight to PCB, you can click that. It'll open up the PCB editor. I'm not going to yet, but yeah. Okay, without further ado, I think we should start on the schematic. So I will be referencing, actually I've got it here. I guess this will be a bit of a follow along for you guys. Okay, so to start, I usually find a good starting point. I'll start with the transistors. The BJTs we're using are, let me go back to this. We're using two N3904s. These are pretty common jelly bean transistors, off the shelf, easy to find, very cheap. They have a specific footprint that's it's defined in their data sheet, which I could actually pull up right now. Normally when you pick a component, you'll know to look at the data sheet and see the symbol and its pinout. In this case, our emitter is pin 1, our base is pin 2, and our collector is pin 3. I don't know how many of you are familiar with BJTs, but it's a very old but common type of transistor. I think later years, if you're in electrical engineering, you'll learn how to use these. But for now, you can get away with just following the data sheet pretty much with almost everything. So we'll follow that. In KiCad, to place a symbol, we will want to go to this icon here, and from that, if you click it, you'll open up a window. Alternatively, you could also press A. That's the shortcut key for it. I'll just stick with the defaults. This is where it loads all of your symbols, as well as the footprints in the background as well. It's got a pretty comprehensive list of symbols. So if you ever have a device, say a simple logic IC, it should typically have it. I forgot how slow this is sometimes.
I have a question.
Go for it.
What is a transistor and why do we need them in our circuit?
Great question. So, a transistor acts like a switch, but also it has different regions of operation. In this case, we're operating them as switches. So it's sort of like a give it power to the base, which is pin 2 in this case, and it'll allow current to flow from the collector to the emitter, or in this case, pin 3 to 1. And then to stop current flow, you remove power from the base, and it'll stop current going through it. These are active devices, so they also have non-linear and they have different regions of operation, like I said. So in some cases, you are able to, say, bias these transistors with a specific voltage, specific current to sort of put them in a certain region of operation where they act as amplifiers. In this case, we're driving them hard, meaning they are going to be either on or off. There is no other in between. Which is usually the case for digital circuits. So with the symbol selection window open, easiest way to find a component is to search for it. I'm going to go NPN. That's the type of BJT we're using. And there it is. However, this is a complicated part. I'm sure I explained it better 2 years ago, but it's been a while. In this case, we're going to want to find a symbol that has the pins in the correct order. And for that, we need to find what's known as an EBC symbol in KiCad. So it's going pin 1 to 2 to 3 is emitter base collector, EBC. And that will automatically have it lined up. So I'm going to go EBC. And you can see here in the symbol, we've got pin 1 on the emitter, pin 2 on the base, and pin 3 on the collector. That's a crucial step. I know I've missed it with a previous design of mine. I had the PCB sent out and created, and then I went to go solder the transistor on, and it didn't work. So it's critical to pay attention to that. With almost every active device with multiple pins, you'd want to consult the data sheet and ensure you have the pin out correct. I will double click that, and then I'll be able to place the symbol. And since our schematic has 3, we're going to place 1. I'm just going to hit Control C. If you don't hit escape, it'll think you want to place another symbol. So, boom, and then I'll paste the last one. I'll just throw them on. Now, following the schematic, we can start wiring stuff up. I typically leave that for after. It's entirely preference. But I think the sooner we get through the schematic, we can move on to the PCB, which is, I find, more fun. So I will start by wiring these guys together where needed, and then we can throw on the resistors, which will be neat. So I'm going to connect that there. And if you guys ever want to pan, if you have a mouse, you can hit click the middle scroll wheel button, and it allows you to sort of pan around. Now, as you guys are drawing that, just to go over some basic symbol drawing patterns you'll see. In some schematics, you might see wires going over other wires with like a little arch. Typically, that's not done in industry anymore. Instead, we use dots. And then where we don't have a connection, we have just a crossover line, sort of like that. So where there is a connection, there's a dot. Where there is no connection, there is no dot. I'll go into sort of a best, I gave out a document that sort of goes over the best practices. In there you'll see sort of the reason as to why industry switched over to this. But it works good, so it's one of the reasons. All right. And then, yeah, okay, let's start with the resistors. To add a resistor, I'm going to go back into my symbol selection. I will clear the filter and I will hit R. We're given the European symbol for a resistor. It is entirely preference which one you use. I will opt to use the US version, which is the squiggly line. This one's common too, though. You'll see it everywhere. I'll double click that to add them in, and in this case I'm going to throw on 4 resistors for the schematic. And I'll just use copy paste to throw on the other 2, 3. All right. And I will start connecting those guys to what they need to be connected to. And if you ever need to draw a wire from not a node where you are able to, you can always hit here or press W to create a wire. Otherwise, you can also create a wire just by clicking here. I forgot to mention. Yeah. So I'll just throw that down there. This guy can go down here. And then these two are our inputs. So we'll add the buttons after that. And all these resistors are going to be connected to the positive terminal of the battery, so I've just connected them all together right here, and then we can add in the battery symbol and the switches, as well as the ground. We'll need that. So, going back to the symbol selection, I will find a switch, probably just SW. And in this case, we've got different nomenclatures for switches. We've got SPDT, which means single pole, double throw. So that'd be a 2 selection switch like that. We want single pole, single throw to create just a push button implementation. So I'm gonna go single pole, single throw. And just like that, that's the button we want. And we want 2 of those. So I'll throw 2 of them in.
Sometimes there's some confused looks. We just want to remind people they can ask questions.
Oh yeah. If anyone has questions.
Yeah, if you have a question, if you're confused, I see you guys are talking with your peers, and I think that's great. But feel free to raise your hand, ask a question, speak out, say, I have a quick question. Or raise your hand and one like Adam or maybe even me, one of our moderators might be able to help you out.
Yeah.
So feel free. There you go.
Yeah, go for it.
Sorry to interrupt.
What does that mean on a switch?
Single pull, single throw, or single pull, double throw. What that means on a switch is every pull is your input, and throws are the amount of outputs. So if you have double throw, then you have 2 outputs that you can switch between. And then single pull would be, you have 1 input switching between those 2. A double pull, double throw, that would basically be 2 single pull, double throws ganged together. So, yeah, buttons are great. Actually, yeah, while everyone else is drawing, it's a great time to ask questions. So if anyone else has any questions, put up your hand. I'll do my best to look up from time to time. But otherwise, let's go into, I guess we should add the battery. That would be a good thing, power source. Symbols for components and power are separated by 2 menus. The ground symbol here just below the symbol up here where you use to find your symbols. This guy allows you to access all of your power related connections. I'm just wondering if the battery is in here. Yep. Except that's not the one I want. Okay, so it is under the symbol. In the symbol editor again. Battery cell. It is a CR2302, so I think that's a single cell battery. Correct me if I'm wrong. But I'll throw that in there. No, I don't want that. Okay. And then I'll just connect that to the power. And then all that's left is the ground connections. So to get the ground connections, that's where we do want to be in the power symbols selection. Now in here we have all of our different common voltages and various options. So for a larger schematic, larger circuit, we might have multiple different voltages that we're operating with. And a lot of these have, like this selection here has a lot of standard values. Other times you might need a more specific value, which I believe they have a global voltage. Otherwise you are able to rename a lot of these to your specific voltage, and it recognizes that as a net. Now I mentioned net. What is a net? I'll explain that right after I add the ground. I should stop getting sidetracked. So I'll just search up ground. GND is the nomenclature for that. And I will throw it right below the battery. And additionally, I'll copy that over. And I'll put one right below this transistor. And I'll put one right below these two switches. Now, what is a net? A net, or a node, usually as they're called in our classes, we'll learn about nodes. They are essentially points where all of your components connect to. So in this case, this net is connected between pin 2 of the switch, pin 2 of our transistor here, and this pin of the resistor. They're all one electrical connection. That there is what we would normally call a node, or in the EDA, a net. Now, nets have their own unique names for identification within the PCB design. And if you want to be able to sort of connect nets across different sheets in your hierarchical, you would usually use the name of the net to correlate them. Meaning if you have two sheets and you have various 12-volt lines, 12-volt sources, say maybe from a 12-volt battery and then a 12-volt power supply, you don't want them to be electrically connected, and if you name them both the same thing, the software will think they're electrically connected. So make sure to give unique names for each node or net. In this case, we don't need to worry about that here, but later on in your own designs, that is definitely a consideration. And that is one of the key reasons you have so many options here for like 12 volt C, L, LF, P. They all have different meanings. This one's one I use pretty commonly, but yeah. So I'm going to connect all the grounds here just to move things along. Any questions as well? Cool. And then the last component, I'm going to throw in an LED so we can see what's happening. So to throw in an LED, I'm just going to go here, symbol editor, or symbol selection, LED. You have so many different options for LEDs. You've got all your RGB stuff. This would be where you look at the data sheet, see which one you're using, find a symbol that corresponds to it. In our case, just a simple LED. And then to rotate, it's usually Control R, I believe. If not, what is it? Is it just R? Okay, cool. I've been using way too many CAD softwares. And they're all just slightly different. You could also alternatively just rotate here, or I believe, yeah, if you hit R, you can rotate. Thanks for that. Okay. And I'm just going to connect point to point, and this guy goes to the output here. Okay. That is the full schematic drawn. However, at this stage, we're missing information still. So we know how the parts are connected. We know how it's going to be laid out, but we don't know what parts we're using. This is where I introduce the options or properties of each symbol. Quick way to access it is just click on the symbol, press E, it opens up the window. Otherwise you can right click, go to this context menu and hit properties. And in here we have our reference designator, our value, and our footprint. Now's a great time to explain what a reference designator is too. A reference designator allows us to understand which part is where, and it's a unique sort of way of identifying a part within a PCB. So if you ever open up like any piece of electronics and you look at the PCB, look at the circuit board, you'll see beside every single component there's a little letter and usually followed by a number. That would be the reference designator. It's unique to that component, and it's how manufacturers, it's how engineers and repair guys, technicians, everything else are able to find parts and be able to put them in the right spot. So in our case, they're automatically placed. You can see all the resistors have R and then the number. The BJTs, our transistors, are usually designated with Q. Diodes or LEDs are with D. Wikipedia has a full list. Switches are SW. And if you ever go to a company and they have their select CAD software and circuit layout editor, they usually have a standard set of reference designators that you use. Most of them follow industry standard though, so same with this software, industry standard. Now let's give these components values. Following along with the schematic, these resistors are going to be 10 kilo ohm. And so we don't fill up a bunch of space with extra zeros, we'll actually use the SI prefixes at the end of the numbers. So a 100 ohm resistor you could write as 100. Some people use 100R. The R is meant to replace the omega symbol. Yeah?
How do you open that up again?
Click the symbol and press E, or here, I'll close out of it and show you. So you can click E like that, or right click, and it's under properties. Right on. But yeah, going back to the SI prefixes, we use R for single unit to replace the omega, just because the omega would show up as like a O or a 0. People get messed up with that. Or you just write it as is. But then you also go up in value with K for 1,000, M for million, so on and so forth. In this case, I'm using a 10K resistor, 10,000 ohm resistor. And I will just go through and add that to each of these. So that's just under the value box here. And this one's a 33K, and this one is a 470 ohm. So this is what I mean by it's 470 ohms. I don't need to add a prefix. Just leave it as is. If I'm going too fast, let me know. I tend to sort of rush through things. Or if I'm going too slow, tell me to speed up. But yeah. Whee. Alright, and then with the resistors done, I'm going to go and move on to the BJTs. Once you open up the properties, I will give this, usually with active components, you'd use their part number in the name. So I'm giving these 2N3904 is the part number for this transistor. And I'll hit OK with that. Now in this case, I'm only going through and naming the parts, but it is not the end of this properties window. We'll be back because we need to assign footprints, which I will go over right after. Yeah. So. You can name the LED too if you want. I'll leave it as LED. We're just going to use a standard 5mm LED part. So no need to go into specifics there. I can name the battery cell though. CR2302, just to specify the type of battery. And if you ever double click any text, you'll get this box, which allows you to change the font size, font type. I mean, I think if you really wanted to, you could do Comic Sans. So there's that level of customization. All right, now on to the more complex stuff. Yes?
Say what the value for the design, I can't.
Which?
The resistors of pop, I can't move right to, I can't.
Let's see, we've got two 10Ks, a 33 kilo ohm resistor, and then at the very end there is a 470. The reason for the values is sort of more or less
Yeah, I just couldn't
to get the circuit functioning. Yeah, no, definitely. And there was a question in the back as well. You had one? Okay, cool. Transistors were 2N3904. Yes, I could stay zoomed in too for the back. I completely forgot. Cool. Okay, I'll stay like this. That should be plenty large. All right, so now with the schematic done, we need to be able to make a PCB out of it. To do that though, we need to assign footprints. So what are footprints? They are essentially the realized mount for your component on the board itself. In the case of our transistor, you can see it's a three-legged component right here in what's called a TO92 package. Now with every component you find, it'll list the package, which is the physical shape, dimension, type of legs. It's a standard way of sort of creating parts. And that package will have a footprint to it. Most of those packages are in KiCad. So I'll start with the transistors because those are the most crucial component. In properties, we can assign a footprint to a symbol by going to this footprint line. And when you click on this window, you have sort of a hamburger icon, books, whatever. Click on it, and it'll open up your footprint chooser. It's the first time I've ever actually read the header on that. So in the footprint chooser, we'd want to find that package. So going back to the data sheet, always consult the data sheet. You can see it's a TO92 package, which if we ever go here, TO-92, there it is. So that's our package. Now there's various different kinds of packages for the same package, if that makes sense. We can go with the default, or in this case, we've also got hand solder, which is a footprint that's optimized for if you're soldering by hand. It is entirely preference which one you choose. If you're unsure though, always make sure to double check the measurements so you don't have any issues when you go get them the boards manufactured. But in this case, I'll go with the default. So I'm going to double click that. It should set it right here, and with that you can hit OK. And the footprint will be set for that transistor. The joy of this is you have to do this with every component. You have to select all the footprints. To speed things up, since I have 3 of the same transistors, I'm just going to highlight this entire line, hit Control C and go through, select the line, paste. Or alternatively, you could select the text and paste the text, and it'll work as well. It's just a path to the footprint. Yeah. So a footprint, it might be better if I show you. So a footprint in the PCB, this window here, you can actually see and preview the footprint. The red is the copper. The yellow is the silk screen. I'll go over this when we go into the PCB editing, but basically each of those circles is a hole that the legs will stick into. So it's the physical, it's your physical mount for the component on the circuit board. Yeah. And actually, yeah. Yes, they were. Some manufacturers will actually pre-bend them, depending on which one you order. In manufacture, from my experience, I spent 2 years manufacturing, 1 year on, we called it the hand stuffing team, where you hand stuff all the through-hole components. What we would do is typically just bend the leg, stick it on to a certain distance and solder it on. But if you do want to be more, like say you don't want to put certain stresses on the component mechanically, you could make your own custom footprint, or I believe if you really wanted to, they might have an inline, yeah. So we could use this actually. Take your pick. But yeah, so you've got different options. On the data sheet, yeah, they are aligned, and I believe at the bottom of every data sheet too, if you get past all the data, they will describe all the dimensions. So yeah, in this case, it would probably be better to use the inline one. Good call. Let's use that. It doesn't really matter if you guys already put the other footprint on. Go with whichever you choose. But going back to the data sheet too, if with your part symbol, if you ever want to attach the data sheet link, you can do that. Like for instance, the 2N3904, if I ever go back to this schematic, say 2 years down the road, and I don't want to have to Google the data sheet, I can paste the link right on the data sheet input there. And when I close out of this, a cool shortcut is you can go here and I believe show data sheet. And if I click that, it'll open up the data sheet. Now on the right side, you can also see it says D. That's the shortcut to that. So if I ever click this and hit D, it opens up the data sheet. I've used this so much and I love it. Makes things so easy. Now I'm going to quickly copy these over to all the other components. There we go. Yeah. And then if everyone has that, I can move on to the resistors. Fairly simple. Yeah, typically when you design a circuit, you sort of have an idea as to what parts you're using. For instance, in my projects, I've got at home a surplus of surface mount components of a certain size for resistors, so I usually just opt to use those. In other cases, you might source the part and it has a certain footprint, such as the transistors. In our case, we're going to use through-hole resistors with a certain footprint. So I'm just going to go R. Yeah, it pops up with arrays. We don't really want arrays. So if you get past all the arrays, you have not bare metal, not radial, power, axial. That's what we want. Axial resistors. I'll actually show you what that looks like real quickly. An axial resistor is, I'm sure you guys have seen it around, but never knew the name. Looks like that. So these are sort of the style of resistors we are going to use. There are other resistors though, such as chip resistors, which are surface mount. These ones are the ones that if you want to scale your electronics down, make them small, you'd want to use chip resistors. They are surface mount though, so they can be tricky to solder by hand. I'll go into sourcing parts right after designing the circuit here, but for now I'm going to go with any of these. Usually you'd select a footprint. These components might have a lot of different components or different footprints. You'd select it based on your size requirements. So sometimes it's better to have, say, those axial resistors stick up and then have a lead bend over and sort of have it vertical versus horizontal where it's a lot longer. So that's what this footprint would be. Or we can move along and use a longer flat layout where you even have different lead lengths that stick on top of the board. But for now, I'll just go with this one. 70 millimeter horizontal. I think that's the right one. I didn't write it down. But that should be, yeah, these all look a lot larger. Yeah, okay, we can roll with that. And you can always attach a data sheet if you have. Yeah. Which one is which? It's all the resistors. It is going to be, let me find it. Oh, what did I do? You could quickly find it by searching R axial. If you go R_axial, you might be able to find here. I'll just do that. Let's see what that. No. R axial. There we go. You have your different selection. I sort of just scroll through until I find the part I want. And in this case, it is DIN 0309. So that's the package name. And it'll be the 70 millimeter horizontal or the 24 millimeter horizontal. I'm going to go with the 70. Seems to be small but decent. Yeah.
Do we use the same one for all four resistors?
Yeah, I'll be using all of them. But it depends on your circuit. Sometimes you might have a resistor that's like 1 watt, very big, and then in which case you don't want to specify, right? But yeah, well, in our case, we're all using the same package, same size resistor, so I'm just going to throw that on. Yeah. Yes. Yeah, it is. I think 12.7 is the pitch between the two holes, right? And then I think the 70, oh, I see, it's 12.70. That's where I got it from. Yeah, 12.70 millimeter, yeah. Good. I missed that. And then I'll paste that in. Paste that in. Paste that in. Okay. All right. Now to take care of some stuff we've been skipping over, the LED is a little bit more special as well, in that the footprint, I'll show you what it'll look like. For the LED, we're going to have a 5mm LED. This style of LED you'll recognize as well if you've ever seen any DIY circuits. It will look something like, yeah. There we go. Yeah, something like that. So a 5mm LED, I'm sure a lot of you might have seen if you've seen entry-level circuits. To find that, yeah. So to find that, we'd want to look at our through-hole LEDs. Actually, a great time to mention this. SMD means surface mount device. We're looking for what's called THT, which is through-hole technology, is the acronym. That means it's going through a hole instead of mounting onto the surface of the board. Other acronyms that are used for SMD would be SMT, surface mount technology. In our case, we're using all THT components. And we're using an LED that is 5mm. So scroll down until you see the 5mm LED. And we're going to use this footprint here. Seems suitable. So I'll throw that on there. Now, how's everyone doing with the footprints? Is that going good? Yeah. The LED footprint is LED underscore D0.5 or 5.0, my bad. It would be that guy there. You can search for it explicitly, or you can, as I do, usually I'll just scroll through. Yeah. What was that? Are you asking like what symbols and footprints go together? Or? I'm all the way up the front. I can hardly hear you. I'm sorry.
Also, out of all the symbols, which symbols have you given footprints to?
Oh, let's see. We still have. Yeah, I'll move on to the other symbols here. So we've got the LED. We've done all the resistors, all the transistors, and then the LED. So all we have left is the battery and the switches. So the battery footprint, I think I used a custom one, which I don't think you guys have. So in this case, I'll just find a footprint and we can roll with it. So I'll just search BATT and find a battery holder. In this case, these are all CR2302 battery holders. I think that's the one. Let me see. going through, these are all footprints for mounts for the little coin cell battery. Yeah.
That's what I was going to ask, that they're the watch batteries.
Yeah, it's the watch battery. So I think this one is the closest to what the PCB was designed around. So I'll roll with it. You guys are free to select whatever footprint for this. But in this case, I'm going to roll with this guy. You can probably search for it by typing in HD or HLD-012-SMT. As long as you're specific enough in the name, it'll pop up. So I'm going to go with that. And hit OK. Okay. I'm going to switch this back. Okay. And then we've got the buttons. With the battery selected, going to the buttons, I'm just going to search up SPST and start scrolling through. Usually what I'll do is I'll find the image or I'll have the physical part. In this case, I'm going to go with a 9mm button. Watch as it gives me an automotive button. Oy, why is the internet so slow? We're not doing textiles. Okay, there we go. That's the button I want. So we're going to use these buttons, specifically that guy, sort of. We have our own part, but it's similar. So it's a little four-legged button. On each side, the two legs are sort of electrically connected. So it's more of a structural thing that they have four. In our case, we'll need to find that specific button. I usually scroll through and look for the 4 pins. SW. I should have expected that. SPST. Switch. There we go. And you scroll through and find, am I in the surface mount? I am. I don't want surface mount. There we go. Wow, is that all we have? Okay. What if going through, and there's a lot of different switches out there, which KiCad has the footprint to. But if we go through, I might find the right one. Would you look at that? It's under push, because it's just a little push button, tactile push button, so I should have expected that. It is a 6mm push button. So we can find that just by typing in SW_push and then find the 6mm. And I'm sure there's different reasons for each of these. I think that's the height of the button itself. But I'm just going to go with the default SW push. And I will copy that over to the other button as well. And hit OK. Yeah. And with that, I think we have all of the footprints set out. So I think from here you are able to create your PCB. But before we do that, I have a bit of extra stuff to cover. I completely glossed over another thing too. Usually with your schematic, wow, I drew it really high up. usually with your schematic, every engineering drawing has a title block. I do a lot of quick prototyping, so I tend to forget entirely about this in my drawings. But when you want to create a full-fledged design, usually you'd want to make sure your drawings are very tidy, very presentable. And with that, the title block is pretty crucial. So to edit the title block, you just double-click on it. I usually go where it says title and double-click on it. And in there, you are able to select the document size, the orientation. I usually keep it as A4 and landscape because every printer uses A4 or letter. So makes it easy for sharing around. You can set an issue date, you can set a revision 1.0 or A. You can give it a title. It can be whatever you want. Company. These are all optional fields to sort of be a bit more professional with the design. But yeah, once you fill out all of that, select it, it'll fill in the boxes. So I thought I'd go over that before I forgot. Let's see, what else is there? That's a neat shortcut. If you guys are tired of doing everything manually, you can also hit Control D and duplicate a part. That would have been convenient. So, shortcuts are amazing, guys. All right, and while I have time, since I'm actually going pretty fast, I was surprised at how quickly this schematic was compared to not last year's, 2 years ago. The last workshop, we had a little bit of a bigger circuit, so it took a lot longer, but in this case, I have time to go over if you ever want to create your own symbols. So, unrelated to our circuit, I'll just open up the symbol editor and I'll show you guys around this. So every symbol, every circuit has, or every part has a symbol, as we all know. And if we ever want to bring in our own components, say, I could probably create a symbol for maybe a vacuum tube, if anyone cares about legacy technology. Those symbols usually don't exist, so we got to create them. I won't actually fully create one, but I'll show you guys sort of the ins and outs of this window. Kind of like the schematic editor, you can create, a symbol. Oh, we got to create a library first. So we need to create a new library. Let's create a new library. I'll make it project specific. You can create a library, say you're using a part across multiple projects. You can create a global symbol. In this case, I'll just do a project. It'll prompt you to create a library file. I usually put this inside my project folder, and I'll call this new symbol. Sure. Every symbol has its depiction and its pins, and pins are how you connect it to the circuit. So in my case, I will want to create a new symbol. I'll call it custom part. I will derive it off of nothing. I'll derive it off of nothing. And I'll give it a reference designator. So if this is, say, an op-amp or a digital IC or anything, I would give it a reference designator U, as that's typical for ICs. Say I'm creating a unique symbol for a resistor, I would set that to R, or say for a diode, I'd set that to D. You could set it to whatever you want to. You could do multiple letters. It's entirely up to you. In my case, I'm just going to go with U. And then we define the number of pins. So say I'm creating a op-amp. An op-amp will have 2 inputs, 2 power pins, voltage plus and ground, or voltage minus, and then it'll have 1 output. So that totals to 5 pins. So in that case, I would go 5. And then go through your selection. Sure. Hit OK. And it gives you your reference designator there. I'll just throw that to the side. And this is where you are able to draw your symbol. I'm not going to try very hard, but you can draw and, oh, this is going to be a lovely op-amp. For those of you who have seen an op-amp, this is going to be a disgrace to every op-amp ever. Okay, actually, you know what? The drawing can be finicky if you're not used to it. Another thing too is if you're drawing and you're annoyed with the grid, you can change the grid size. And I am in mils. I want to be in millimeters. But you can change the grid size. It allows you to draw a little bit finer. And with that, you can create masterpieces like this one. That's a lovely op-amp. Sure. That is a very quick rendition of an op-amp. Now to set the pins, this is the important part with a schematic symbol, is setting its pins. To do that, you'd press this here, and you can give it a pin name and a pin number. The pin number correlates to the actual package. So say you have your op-amp is in a certain package and your voltage plus is on pin 1. You'd set that to 1. And then the pin name, I could say V++ or VDD, right? Whatever name you want to give your pin, you can. And then you can throw it on there. Yeah. You can make all your connections however you want. Typically you'd connect the line to make it look tidy. I'm just rushing through this to sort of let everyone dip their toes in. Down. No. No. Wrong one. Up. There we go. No, wait. Down is correct. Okay. The grid, always the grid. Anyway, yeah. So you'd sort of just lay out pins as you go and do all your outputs. This symbol will never be accepted into anything. It is very, very artistic, but it's what we call a rushed job. So that's a symbol editor. I don't know if it's really just putting down the pins, making sure the pin numbers are correct. If you have a simple box that you want to do, you can also use a rectangle, draw a box, and have all of your pins going to it. So say VCC and pin number 1, have that go to the left. And you can put that sort of like that, and do another one, pin name A2. Do that. You can do that with your block. So yeah, any questions regarding the symbol editor? I sort of winged it on the explanation, but it's a good introduction into that. And then when you complete your part, you're able to save it and bring it in to your schematic. I think I named it custom. Yeah. See? Now we can bring it into the schematic. So I won't, just because it's not really an actual part. But yeah. I'm just thinking, I gotta save something for all the other sessions. So I'm going through all the more tedious stuff. Yeah, I think that's really all I have for this session. All right, so with that, I will go through some of the other stuff, mainly this guy. So with schematic diagrams, there's always best practices that you can employ. And in one of the documents that were emailed to you, we've got schematic design best practices. It's best practice, it's not a requirement, but usually following a guide with all of your circuits, all of your schematics, produces a very tidy and consistent result. So just going through this document, I don't think I have them downloaded. Yeah, there we go. Okay. So this guy here, this document goes through just the basics of drawing a schematic, such as utilizing the snap grid, changing the grid size so you can kind of move things around nicely. Signal and voltage flow. So how you draw the schematic, you typically don't have signals flow right to left. You'd want them to go left to right, kind of the same way we read. And then we've got the different kind of paper sizes to use, texts and fonts, make sure they're readable. Text placement, so around a component you can place text in different ways depending on the orientation. Junctions, this one I touched on earlier. In industry we don't use the hoop over symbol anymore. We use the dot, and typically we don't do plus junctions, 4-point junctions. We tend to keep it to T junctions, and the reason for that is that little dot, if you reprint a document, scan it, print it, scan it, print it, you receive you get what's called generation loss, and sometimes that dot can fade away, or maybe someone will miss it. It's a lot harder to miss a connection if it's a T, because it makes sense that that's a connection. So we typically do junctions sort of like this one here. I break that rule sometimes though. I'll do a cross. It's entirely up to you. Symbol consistency for the resistors. If you choose the US resistor, it makes sense not to use the European throughout the whole schematic. So stay consistent. And yeah, drawing pins. This document covers a lot of stuff. I'm not going to actually read it out, but yeah, there is stuff there. And then covering, this one's regarding the way we write down component values. So in this case, you could use, like, for a 10K resistor, 10,000 ohm resistor, we usually do 10K. And sometimes we actually put that SI unit prefix where the decimal place is, just so that it's easier to read and harder to sort of get confused on. So in this case, like a 2.2 kilo ohm resistor would be a 2K2, or a 3.3 mega ohm would be 3M3. Same thing is done with capacitors and inductors, as shown here. Yeah, this goes into a little bit more on that. And then reference designators. I actually included a list of reference designators, so you can read through it. Usually these are the letters that go before like the R01 or R02, whatever else, for resistors, and we've got for capacitors, ferrite beads, transformers, all of the different components you might use. Yeah, that's pretty much an overview of that document. In the next session, I will go over sourcing parts, sort of the process on that. Because normally when you design a schematic, you'd want to source parts with it. In this case, we already have an idea of what parts we're using, but in other cases, we might need to find parts. And then, yeah, next session we can start on the PCB. I think that should be quite fun. But that's pretty much all I've got for today. I don't know. Any questions? Anything really on whatever you guys want to know? If we're good, then yeah. And that's.
Okay. I think I'm louder if I just yell. So I'm just gonna yell. Little bit of info. We're gonna email out tonight's stuff, and if you got lost on the design, we'll also probably email you like a step file up until tonight. And then if you still haven't collected your $5, if you paid $20 for this workshop, please come find me. Otherwise,